Hello and welcome to week 5 of our class about differential equations. This week we're going to start talking about second order and higher order linear differential equations. And we will spend 3 weeks talking about this topic. This week we'll cover the first 3 sections. Section 3.1 is really an introduction. Homogeneous equations with constant coefficients. Section 3.2 was discussed some theory, talk about fundamental sets of solutions, and then section 3.3 will discuss what happens if we have complex roots of the characteristic equation. We're going to be discussing equations of this form. Either y double prime plus some function of t y prime plus some function of t y is some function of t. We have a y prime on its own, a y prime on its own, and a y on its own. And these functions of t can be any function. Or we could write this in a different way. Some function capital P, y double prime, plus some function capital Q, y prime, plus some function capital R, multiplied by y is equal to some function capital G. These equations are linear and they are second order. If the function g on the right, either small g or capital G, is always equal to 0, then the differential equation is called homogeneous. If g is not always 0, then the equation is called non-homogeneous. Our first section is about homogeneous equations with constant coefficients. Homogeneous, remember, means equal to 0. So we're going to be looking at equations like this. Homogeneous means that we have equal to 0, and coefficients are this a, this b, and this c. And we're going to just suppose that these are numbers. First example, solve y double prime minus y is equal to 0. We're looking for some function that when we differentiate the function 2 times, we still get the function. Y needs to satisfy that 2 derivatives of y is just equal to itself. Let's think about what sort of functions could satisfy this. What about e to the power t? How does this work? If we take e to the t and we differentiate it, we get e to the t. Differentiate again, we still get e to the t. This is a function which we can differentiate 3 times and it's equal to itself. This is not the only function that happens that this is true for. What about e to the power minus t? What happens if we take e to the power minus t and we differentiate 2 times? The first derivative would be minus e to the minus t. Differentiate again, we get plus e to the minus t. So yes, this also satisfies the equation. What about if we took a linear combination of these 2 functions? I suppose c1 and c2 are just some constants. And let's suppose we looked at c1 e to the power t plus c2 e to the power minus t. If I differentiate this function 2 times, what do I get? And the answer is we get the same function. In fact, this is the general solution of the differential equation. This includes every single answer to this. Every single solution to this differential equation can be written as the form constant e to the power t plus constant e to the power minus t. Now an initial value problem. Solve the same differential equation, but now with two initial positions. Y of 0 is equal to 2, y prime of 0 is equal to minus 1. This initial value problem has a second order differential equation. Here it is. And it has two initial conditions. And you'll notice the number 2 appears twice. It's a second order equation, and it has two initial conditions. And this is a rule. The number of initial conditions we need is always equal to the order of the equation. When we look at third order equations, we will need to have 3 initial conditions. We had a fourth order differential equation. We would need to have 4 initial conditions, and etc. We know that c1 e to the power t plus c2 e to the power minus t is the solution to the differential equation. And again, the number 2 is appearing. Second order equation, 2 initial conditions, and look, 2 constants, c1 and c2. We are looking for the solution which passes through the point 0, minus 2, because when x is equal to 0, y is equal to 2. And we're looking for the solution which has slope equal to minus 1 at this point. So we need to find the constant c1 and c2 which satisfy these rules. Using the first initial condition, with t equal to 0, we must have c1 plus c2 is equal to 2. And we need to differentiate our solution. Y prime is the derivative of c1 e to the power t plus c2 e to the power minus t. And of course, this is c1 e to the t minus c2 e to the minus t. And then we set t equal to 0. We know that y prime of 0 must be equal to minus 1. And we now know that if t is equal to 0, we get c1 minus c2. So we get another equation. c1 minus c2 is equal to minus 1. We have a linear system of 2 equations for c1 and c2. As you know how to solve these from linear algebra, so let me just tell you that to satisfy these 2 equations, we need to have c1 is equal to a half and c2 is equal to 3 over 2. As soon as we know c1 and c2, we can write down the solution to the initial value problem. Half e to the power t plus 3 over 2 e to the power minus t. Now let's go back to the general equation. ay double prime plus by prime plus cy is equal to 0, where a, b, and c are some numbers. In the previous example, we used exponential functions in our solution. So we can make a guess now. Maybe the solutions are always exponential solutions. That's a reasonable guess to make. Let's see what happens if we use exponential solutions. To make a guess, and we're going to guess that y is equal to e to the power rt, some number r which we don't know yet. And we're going to calculate derivatives, y prime and y double prime, and we're going to put these into the differential equation. And you'll find that ay double prime plus y prime plus cy, everything includes e to the rt, so we can take this out. And we are left with ar squared plus br plus c. And this must be equal to 0. Now, e to the rt, you will immediately notice this function, e to the rt, is something like this. This function is never equal to 0. This is not equal to 0. We know this. If this whole thing is equal to 0, then that means the first part must be equal to 0. So we must have that AR squared plus BR plus C is equal to 0. We have two equations here, the differential equation and this equation we've just made. The second equation is called the characteristic equation of the differential equation. And the rule that we've just shown on the previous slide is e to the power RT solves the differential equation if and only if number R solves the characteristic equation. And this is the theorem we use to solve equations like this. Let's look at this characteristic equation. AR squared plus BR plus C is equal to 0. This has two roots, minus b plus or minus the square root of b squared minus 4ac over 2a, as we know from high school. And there's three possibilities for R1 and R2. Maybe they're real numbers and they're different. Maybe they are complex conjugates. Or maybe they're real numbers but repeated. Maybe we have R1 is equal to R2. These three cases we need to study separately. First, we're going to study the first case. At the end of today's lesson, we'll study case 2. And the third case we were going to save for next week. So let's look at the first case. Let's suppose the two roots are real numbers and let's suppose they're different numbers. In other words, from the equation on the previous page, we must have that b squared minus 4ac is a positive number. In this section, we're going to be looking at equations where b squared minus 4ac is a positive number. And we know that e to the power r1t and e to the power r2t are both solutions to the differential equation. And if we know two solutions, then we know that a linear combination of these two solutions is also a solution. This function in the orange box is called the general solution to 1. So what we're going to do is we're going to solve the characteristic equation to find R1 and R2, and then we're going to write down the solution in this form. For example, solve y double prime plus 5y prime plus 6y is equal to 0. The first thing we need to do is to write down the characteristic equation. And we just copy the numbers. If we look at the differential equation, I have a 1, a 5, and my characteristic equation must have a 1, a 5, and 6 in. Just copy the numbers down, change y double prime to r squared, change y prime to r, and remove y. This is our characteristic equation. And we can factor this because it's this first example. I've given you an easy equation. This is r plus 2 multiplied by r plus 3. So now we know the two roots. The two roots must be minus 2 and minus 3. As soon as we know the roots of the characteristic equation, we can write down the solution to the differential equation. R1 is equal to minus 2, so we put a minus 2 just here. R2 is equal to minus 3, so we put a minus 3 here. And that's all we need to do to solve the second order linear differential equation. Now let's do an initial value problem. We're using the same differential equation from the previous example. We already know the solution to this equation. And now I'm putting two initial conditions. Y of 0 is 2, y prime is equal to 3. We already have the general solution to the differential equation. We just need to find the constants C1 and C2. First of all, if we take our differential equation with t equal to 0, we get 2 is equal to C1 plus C2. So C1 must be 2 minus C2. We also differentiate y prime. Minus 2 C1 e to the minus 2t minus 3 C2 e to the minus 3t. And then set t equal to 0. And we find that we must have 3 is equal to minus 2 C1 minus 3 C2. After we solve these two equations, we can find that C1 must be 9 and C2 must be minus 7. Then we can write down the solution to the initial value problem. This must be 9 e to the power minus 2t minus 7 e to the minus 3t. Question in the chat is homework 1 still available to solve? And the answer is yes. I'm setting all of the deadlines to 10th of January. So it's still available for everybody, even if you registered late as well. However, I just lost connection and then I'm back. So I'm going to repeat what I just said. Question in the chat is homework 1 still available to solve? The answer is yes. The deadline for each homework I'm setting to the 10th of January, so that students that register late are not disadvantaged. However, please don't wait until January before you save the homework. But homework is to help you learn the material each week. So the aim of the homework is that you will solve one homework each week to follow the course and to check if you understand each week's lesson. And if you don't understand something, to ask me for more help on that topic. But technically, you won't lose any marks if you wait on the homework. You won't lose any marks if you really want to wait till January before you solve them. Next example. Solve 4y double prime minus 8y prime plus 3y is equal to 0 with the initial conditions y of 0 is equal to 2, y prime of 0 is equal to a half. First thing we do is we write down the characteristic equation. Again, we just take the numbers 4 minus 8 and then plus 3. So we have 4r squared minus 8r plus 3 is equal to 0. And I'm going to use the quadratic equations formula to solve this. Two roots are minus b plus or minus the square root of b squared minus 4ac over 2a. If we put the numbers in, we find that the two roots are 3 over 2 and a half. As soon as we know these, we can write down the general solution to the differential equation. C1 e to the power 3 over 2t plus C2 e to the power of a half t. To finish this example, all we need to do is we need to find the constants C1 and C2. And I'm going to leave this for you to check. Please check that using the initial conditions, we must have that C1 is minus a half and C2 is 5 over 2. Put these into the previous equation. The solution to the initial value problem must be minus a half e to the power 3t over 2 plus 5 over 2 e to the power t over 2. So let's summarize. Solve the second order linear differential equation with homogeneous with constant coefficients. We need to find two linearly independent solutions. And then the general solution is a linear combination of these two. We've looked at case 1. If the roots of the characteristic equation are both real numbers and they're different numbers, then our two solutions are e to the power r1t and e to the power r2t. And then the general solution to the differential equation is a linear combination of these two functions. Constant c1, and then the first function, e to the power r1t, plus a constant c2, and then the second function, e to the power r2t. If the roots are complex numbers, we're going to do this later today. If the roots are repeated, we will look at this case next week. Section 3.2 is called Fundamental Sets of Solutions. I want to discuss some of the theory briefly. I'm going to be looking at the differential equation y double prime plus some function p of t y prime plus some function q of t y is equal to 0. This is a homogeneous linear second order ordinary differential equation. And because we're going to be writing this a lot, it's useful to have a short type of notation. I'm going to define an operator capital L with two derivatives plus pt, one derivative plus qt. What this means is this operator L of y, if I write L of y, that's the same as writing two derivatives of y, pt, one derivative of y plus qty, or y double prime plus pt y prime plus qty, which means that the differential equation at the top you can write in the short form L of y is equal to 0. And that will just save some notation. Anytime you see me write L of y is equal to 0, I mean this differential equation. Theorem. If y1 and y2 are both solutions are L of y is equal to 0, then every linear combination C1 y1 plus C2 y2 is also a solution of this differential equation, any constant C1 and C2. This is a straightforward proof. Let me go through this very quickly. If we start by assuming that L of y1 and L of y2 are both equal to 0, then we can calculate L of y, or L of C1 y1 plus C2 y2. Now if we go through this, we find that capital L is a linear operator, so the same as C1 capital L of y1 plus C2 capital L of y2. This is why I'm using the capital L, because it's linear. But L of y1 and L of y2 are both 0, so this is just 0 plus 0 or 0. So here's the idea. We're going to find two solutions, and then we're going to take a linear combination of them to get the general solution. We also need something called the Wronskian, which is named after a Polish mathematician called Wronski. You will remember this hopefully from the linear algebra course. In this course, we're going to use the Wronskian. Capital W is determinant of 2 by 2 matrix y1, y2, y1 prime, y2. And the key theorem is, suppose we have two solutions, y1 and y2. Let's suppose they both solve our second order linear differential equation. And suppose that the Wronskian at time t is not equal to 0 for some t. In other words, let's suppose at least at one point the Wronskian is not equal to 0. Wronskian doesn't have to be non-zero everywhere, it just needs to be non-zero at least one point. Then the set containing C1 y2 plus C2 y2 contains every solution of the differential equation. Because this formula contains every solution to the differential equation, this is called the general solution to the differential equation. And in this case, we say that y1 and y2 form a fundamental set of solutions to the differential equation. For example, show that t to the power of half and t to the power minus 1 form a fundamental set of solutions to this differential equation. 2t squared y double prime plus 3t y prime minus y is equal to 0. And this is, I'm only interested in t greater than 0 because we have a t at the front. To answer this question, we need to show three things. We need to show that y1 is a solution to the differential equation. It can't be a fundamental set of solutions if it's not a solution. We need to show that y2 is also a solution to the differential equation. And we need to show that these two solutions are linearly independent. In other words, we need to show that the Wronskian is not equal to 0 somewhere. So first of all, let's look at y1. We can take the differential equation and put y1 into it. In other words, we're looking at t to the power of a half in each place. 2t squared, and then two derivatives of t to the power of a half, plus 3t, t to the power of a half prime, minus t to the power of a half. And when we calculate this, we get 0. Therefore, y1 solves the differential equation. We can do the same thing for y2. Now put t to the power minus 1 into the differential equation and check it. When we do this calculation, again, we get equal to 0. This proves that both y1 and y2 solve the differential equation. There's one more thing we need to do. We need to check if y1 and y2 are linearly independent. To answer this, we calculate the Wronskian. The Wronskian of y1 and y2 at time t. We use our formula, determinant of the 2 by 2 matrix y1, y2, y1 prime, y2 prime. Put everything in, and we get minus 3 over 2, t to the power minus 3 over 2. And because I said t must be positive, this must be not equal to 0. Because this is not equal to 0, y1 and y2 are linearly independent. And then we've done everything we need to do. y1 solves the differential equation, y2 solves the differential equation, and y1 and y2 are linearly independent. Therefore, y1 and y2 form a fundamental set of solutions to this differential equation. There are some problems like this in the lecture notes for you to practice with. Our final topic for today is complex roots of the characteristic equation. I'm going to go back to homogeneous linear second order differential equation with constant coefficients. In other words, ay double prime plus by prime plus cy is equal to 0. And now we're going to suppose that we're in case 2. We're going to suppose that b squared minus 4ac is strictly less than 0. That's going to give us complex roots of the characteristic equation. In fact, the two roots of the characteristic equation are going to be complex conjugates. And I choose to write them like this. R1 I'm going to write as lambda plus I mu, and R2 I'm going to write as the minus I mu, where lambda and mu are real numbers. And we have the corresponding two solutions. E to the power R1t, or e to the power lambda plus I mu t, and our second solution is e to the power R2t, which is e to the power lambda minus I t. But you're perhaps wondering, what does e to the power of a complex number mean? We have a formula for this. E to the power of a complex number, lambda plus I mu t, is equal to e to the lambda t cos mu t plus I e to the lambda t sine mu t. Why are we using this formula? Let me show you. Note what happens if we differentiate this. Calculate the derivative of e to the power r1t. That's the same as saying the derivative of e to the lambda t cos mu t plus I e to the lambda t sine mu t. We can calculate this derivative using the product rule. First, if we differentiate the first e to the lambda t, we get lambda e to the lambda t, then multiplied by cos mu t. Then I want to differentiate cos mu t, get minus mu sine mu t, and then do the same for the second function. I is just a number. We can ignore I when we differentiate, just as we would ignore any other number. If, for example, I had the number 7 just here, and we would just ignore this when we differentiated. We differentiate e to lambda t to get lambda e to the lambda t. Differentiate sine mu t to get mu cos mu t. Group together the cos terms and the sine terms. We have lambda plus I mu multiplied by e to the lambda t cos mu t. And for the sine terms, these ones in the middle, I have I lambda and minus mu. What's I squared? Remember, I squared is the same as minus 1. So instead of minus here, I could write plus I squared, and then I could factor out an I and leave an I. Now I have lambda plus I mu here and lambda plus I mu here. Let's take this out. Lambda plus I mu I take out, and what are we left with? We're left with e to the lambda t cos mu t plus I e to the lambda t sine mu t. This looks familiar, right? This is what we started with. So what we really have is R1 multiplied by e to the power R1t. Even if R1 is a complex number, still the derivative of e to the power R1t is equal to R1 e to 1. Good. This is why we use this formula. This is why this formula makes sense. We have two functions, and these are not the functions that we have e to the power lambda plus I mu t and e to the power lambda minus I mu t. But these are functions which map from R to the complex numbers. In other words, I mean, if we take a real number t and we put it into the function, then we receive a complex number. And this is usually not useful for us. When we're trying to solve our problems, we want our answer to be a real number, a real function. So we want to have two functions which map from the real numbers to the real numbers. And what we're going to do is we're going to look at these two functions. Function u is going to be a half y1 plus y2. In other words, it's going to just be the average of y1 and y2. And let me remind you, y1 is a solution of the differential equation, y2 is a solution of the differential equation. By one of the theorems in section 3.2, every linear combination of y1 and y2 is also a solution of the differential equation. If I do half y1 plus y2, this is a linear combination of y1 and y2. This is still a solution of the differential equation. And for my second function v, I want to look at 1 divided by 2i, y1 minus y2. You will soon see why I'm choosing 1 divided by 2 and 1 divided by 2. Again, 1 over 2i is just a number. We have a linear combination of y1 and y2, so this is still a solution of the differential equation. Put the formula in. Go through the first one first. We have half y1, so half e to the lambda t cos plus I sine, and then a half e to the lambda t cos minus I sine. We have plus sign and then minus. These are going to cancel out. And we're left with a half cos plus a half cos. A half plus a half is 1. We're left with e to the lambda t cos mu t. For the second function, I think there's a mistake here. Should be an I just here. Should be an I just here. Again, put y1, y2 in. 1 over 2i, y1, minus 1 over 2i, y2. I have plus 1 over 2i cos, and then minus 1 over 2i cos. So these two will cancel out. And there's minus and minus, minus and minus. Two minuses become plus. We have sine plus sine. In other words, we have 1 over 2i, and then 2i e to the lambda t cos mu t. The 2i cancels with the 2i, and we're left with e to the lambda t sine mu t. These two functions u and v both map from the numbers to the real numbers. As I said earlier, they both solve the differential equation because they're just linear combinations of y1 and y2. But are these two functions linearly independent? To find out, we calculate the Wronskian of u and v. Using the formula, determinant of the 2 by 2 matrix u, v, u prime, v prime Put everything in, and we end up with mu e to the 2 lambda t. An exponential function is always not equal to 0. Because we have complex numbers, lambda plus or minus I mu, mu must also not equal to 0. So the Wronskian must not be equal to 0. Therefore, u and v are linearly independent. So we have two solutions, u and v. U and v both solve the differential equation, and u and v are linearly independent. This means that u and v form a fundamental set of solutions. And after we know our fundamental set of solutions, we can write down the general solution to the differential equation. If we have complex roots of the characteristic equation, then the general solution of our differential equation is going to be some constant c1, e to the lambda t cos mu t, plus some constant c2, e to the lambda t sine mu t. So we're going to, let me say how we're going to solve these differential equations. We're going to write down the characteristic equation and find the roots of the characteristic equation. This will give us lambda and mu. As soon as we know lambda and mu, we can use the formula in the orange box to write down the solution to the differential equation. Let's do one. Solve y double prime plus y prime plus y is equal to 0. First, we write down the characteristic equation. What numbers do we have? There's the number 1 plus 1 plus 1. So the characteristic equation must be 1, 1, 1. 1r squared plus 1r plus 1 is equal to 0. And we calculate the roots of this characteristic equation. Using the formula, that's minus 1 plus or minus the square root of 1 minus 4 divided by 2. 1 minus 4 is equal to minus 3, which I can write in the form minus 1 multiplied by 3. Because the square root of two numbers, square root of say a, b, is the same as the square root of a multiplied by the square root of b. This is the same as the square root of minus 1, which is I, multiplied by the square root of 3. In other words, we get minus a half plus or minus I, square root of 3 divided by 2. And we can read off lambda and mu. The first number, which here is orange, is lambda. The second number, which is green, doesn't include the I, just the number, is mu. Lambda must be minus a half, mu must be root 3 over 2. As soon as we know lambda and mu, we can write down the general solution of the differential equation. Some constant c1, e to the power lambda t, which here is minus t over 2, cos mu t, which here is cos root 3 over 2t. And then we have the same thing, but it's cos we put sine. Constant c2, e to the minus t over 2, and now sine root 3 over 2t. And this is it. This is the solution to this differential equation. All fits on one slide. This is all I need to do to solve this differential equation. Let's do another one. Solve y double prime plus 9y is equal to 0. This one's even more concise. I'm starting with the characteristic equation, which here is r squared plus 9 is equal to 0. And because this is easier, I don't need to use the quadratic equations formula. I can straight away factorize this into r minus 3i, r plus 3i. In other words, we must have that r is plus or minus 3i. Remember, we're looking for r is equal to lambda plus or minus I mu. From this, we can see, oh, lambda must be 0 and mu must be 3. There's a mistake here, of course. This should be 3. As soon as we know lambda and mu, we can write down the general solution to the differential equation. General solution to this differential equation is C1 cos 3t plus C2 sine 3t. You would normally have e to the lambda t here, but of course, if lambda is equal to 0, that's the same as e to the power 0 or 1, which we don't need to write. So it's just C1 cos 3t plus C2 sine 3t. And this is it. How many sentences is this? 2 sentences to solve a differential equation. Now an initial value problem. Solve 16y double prime minus 8y prime plus 145y is equal to 0, with the initial conditions y of 0 is minus 2, y prime of 0 is equal to 1. Let me run through the method straight away. First, we need to find the general solution of the differential equation. We'll write down the characteristic equation and then find the roots of the characteristic equation. As soon as we know the roots, we know the solution to the differential equation. And then the final thing we need to do is choose the constant so that the initial conditions are satisfied. So first of all, the characteristic equation. 16r squared minus 8r plus 145 is equal to 0. Calculate the roots. I'm going to skip through this calculation. I'll leave this for you to check later. Do check it because you'll notice I do make mistakes when I'm typing this. So do check this and let me know if there's a mistake here. Let's assume for now that this is correct. 1/4 plus or minus 3i. As soon as we know this, we know that lambda must be 1/4, mu must be 3, and then we can write down the general solution to the differential equation. Constant C1, e to the power t over 4, because lambda is 1/4, cos 3t, because mu is equal to 3, and then plus C2, and then almost the same function, but just with sine instead of cos. Out of habit, I write cos in the first function, I write sine in the second function, but it really doesn't matter. If you want to put sine in the first function and cos in the second function, you'll still get the correct answer to an initial value. I just write cos before sine just because C becomes before S in the alphabet. So it's for me, this is alphabetical order. But it really doesn't matter. Next, we need to find the constants C1 and C2. We need the derivative of y prime. You can check if this is correct or not. And then we put in t is equal to 0. First of all, y0 must be minus 2. If I put t is equal to 0, e to the power t over 4 becomes 1. Cos 3t becomes 1. Sine 3t becomes 0. So everything in the second half is 0. And we're just left with c1. c1 must be minus 2. y prime must be equal to 1. Let's go through this. E to the power t over 4 is 1. Cos 3t is equal to 1. Sine 3t is equal to 0, so this is all 0. Again, sine 3t must be 0. This is all 0. E to the t over 4 is 1. Cos 3t is equal to 1. We're left with a quarter c1 plus 3c2, or minus a half plus 3c2, so c2 must be 1/2. Then we can write down the answer to this problem. The solution to this initial value problem is minus 2 e to the power t over 4 cos t plus a half e to the power t over 4 sine 3t. And this is the answer to this problem. Just in 2 pages, 2 slides for me. First, I find the general solution to the differential equation, and then I find C1 and C2, and then I'm finished. I can write down the solution to the initial value problem. And if you're interested, this function, the solution to this initial value problem, looks like this. So let's summarize. Somebody's just discovered that you can write on the screen whenever you want to. Okay, so to summarize, to solve a linear, homogeneous, second-order differential equation with constant coefficients, we need to find 2 linearly independent solutions, and then the general solution is a linear combination of these 2 functions. We've looked at case 1 and case 2. Case 1, which we did earlier today, if the roots of the characteristic equation are different real numbers, then the 2 functions that we want, e to the power r1t, r2t. If the 2 roots of the characteristic equation are complex conjugates, then the 2 functions that we want are e to the lambda t cos mu t and e to the lambda t sine mu t. Case 3 we haven't done yet. Case 3 we'll do next week. And this is the end of today's lesson. Do you have any questions? Question is, do I mind you sending questions through this discussion board? Certainly not. I'm checking the discussion board every day. If you have a question, ask me through there, and hopefully within 24 hours I'll give you an answer to it. Or perhaps another student will answer your question if you get there. Okay, so as always, you're welcome to leave whenever you wish. I'm going to take a 10-minute break and then I'll come back to see if there are any questions. If you think of any questions later, you can ask me through the discussion board. Question is this is my first lesson. Are we done, or we have another hour? We are finished the lecture. Officially we have 2 hours, but the second hour is for questions and answers. If you have questions, you can ask them to me in the second hour, or if you don't have any questions, you're welcome to leave if you wish.